So we're going to be using some of the units that IB loves to use with the negative exponent to indicate that it is being divided by, so that your numerator is being divided by that. So I just wanted to share the XKCD comic from a while back that tells us that you are all fancy scientists because you're going to be using that notation. All right, so what I want to talk about today is solutions and concentrations of solutions. So you know a lot of this stuff already, either because you've talked about the idea of a solution in Honors Chem, or you may have already used some of this terminology, but just to kind of take it from the ground up. A solution is a homogeneous mixture, meaning it's the same all the way through. You don't have lumps or chunks or layers or anything like that. Technically, it's also a clear solution, something that you can see through, but that's not always the case. And a solution is made up of a solvent and a solute. The solvent is whatever you have more of. And that's usually going to be something like water or alcohol or something like that. And the solute is usually going to be some kind of powder or pellet or something that you're dissolving into the solvent. Okay, not always. We can have two liquids. We can have a solute that's a liquid being dissolved in a solvent that's another liquid. You can have gas solutions of gases. So the air that you're breathing right now is a solution of a bunch of different gases, where one side of the room doesn't have more oxygen than the other side of the room. It's all pretty evenly mixed. Now, granted, right in front of your face is probably a little more carbon dioxide because you're breathing it out and a little bit less oxygen. But for the most part, it's an evenly mixed solution. So the solvent, again, is the thing that we have more of. The solute is what we have less of. And when we talk about concentration of the solution, we're saying how much stuff do we have in that volume of, how much of our solute do we have per volume of solvent, of the total volume of the solution. And you're 99% of the time, you're going to express it in terms of moles per cubic decimeter. This is the same as saying moles per liter, because decimeters cubed are the same thing as liters. And centimeters cubed are the same thing as milliliters. Let's see if the pen will work. Yay, we have pen. So our this is basically saying moles per decimeter cubed. We sort of have pen. The negative sign just means it's on the bottom. Okay, so you're dividing by that. A decimeter cubed is equal to 1 liter. One centimeter cubed is equal to 1 milliliter. IB is going to use these. They're not going to use liters and milliliters because the cubic centimeter, cubic decimeter is the standard international unit for volume, not liters and milliliters. I grew up on liters and milliliters and spent, more than 20 years doing research with liters and milliliters, so it's really hard for me to switch. If you, on a paper 2 question, I've been told that on a paper 2 question, if you give your answer in milliliters and not centimeters cubed, as long as the units are correct, it won't be marked wrong. However, they will give you stuff and they will ask for things in the questions in this format. And so you need to be able to recognize that as moles per liter or moles per cubic decimeter. The other thing that we use, the other sort of unit designation that we use as a shortcut is capital M. So that means molar, and it means moles per liter also. And that is what you're going to see on any solutions that you see in here. Usually in chemistry, we don't talk about percentages, we talk about molarity. So in the back over there, I standardized a sodium hydroxide solution for anybody who's doing an acid-base titration, and it came out to 0.74 molar. And that's what I wrote on the label. It's 0.974 M NaOH. Okay, so that's what that means, is moles per liter. One milliliter is, or sorry, 1 liter is 1,000 milliliters. 1 decimeter cubed is 1,000 centimeters cubed, right? So that is times 1,000. And this is going to be divided by 1,000. Okay. The only time we in the U.S. generally use centimeters cubed for anything is in medicine. If you've ever used a syringe, it usually gives the volume in cc's. Or you may have heard on a Grey's Anatomy episode or something, like, give me 2 cc's of atropine or something. And they mean cubic centimeters, which is the same as milliliters, but that's the standard for syringe delivery and sort of medical delivery of drugs. So that's where you've heard that before. All right, so on page 17, this is where you get a bunch of formulas for calculating concentration. And the main one that you're going to use is this one, moles per decimeter cubed. That is what almost everybody uses when we're talking about concentration of solution. It's almost always what you're going to be given the concentrations of solution as in a problem. There are also questions in the question bank asking you for what is the concentration in moles dm to the negative third. And so you have to be familiar with that. You have to be comfortable with that. But basically what we have is a very simple equation. The concentration is how much stuff over how much volume. And you need to be able to manipulate that equation like you would any algebraic equation to solve for concentration, to solve for volume, to solve for moles. There are also a couple of situations where you would want to use 2 other methods of giving portraying the concentration. One is grams per decimeter cubed, or grams per liter, rather than moles per liter. And occasionally in parts per million, which is basically a mass over mass equation times 10 to the 6th, okay, times a million. So that is going to give you that. If you've heard parts per million or ppm, seen ppm, a lot of times in environmental systems, they'll talk about parts per million of a pollutant in your water system, something like that. When they talked about the lead pipes in Flint, Michigan, there was talk about how much lead is in the water. Well, this many parts per million, and that's kind of what they would use that for. But again, 99% of the time in chemistry, you're going to be talking about molarity in terms of moles per liter. Okay. So let's do an example. Let's look at an example question of something that you might be asked to do, or something that might be relevant to your IA if you are doing anything with any kind of solution. So the question says 50.0 grams of sodium chloride are dissolved in 100 centimeters cubed, so that's 100 milliliters, of water, which is then made up to 500 centimeters cubed in a volumetric flask. Some of you may be familiar with volumetric flasks, some of you may not. So this is a volumetric flask. This is, in fact, a 500 milliliter volumetric flask. A volumetric flask has the big bulb on the end for holding the majority of the solution, and then it's got one line, just one. So the only thing I can measure in this flask is 500 milliliters. I can't measure 450 or 250 or anything like that. All I get is the one line that tells me when your meniscus is, the bottom of your meniscus is at this line, you have 500 milliliters of whatever you're measuring, okay? And so typically, when you're making up a solution, if you're mixing magnesium carbonate with isopropyl alcohol, for example, like Amaya's going to be doing, you're going to want to know how much you put in and measure it as precisely as possible. Volumetric flasks are a great way to be precise about volume. The uncertainty here is plus or minus 0.20 milliliters. So 0.2 milliliters is the uncertainty here. That's much lower than any of our graduated cylinders. So if you have an experiment that requires very precise concentrations, volumetric flasks, volumetric pipettes are what you're going to want to use. But remember that your solute, the stuff that you're dissolving in the solvent, so in this case the sodium chloride that we're dissolving in the water, that is going to take up some space. I mean, it's going to look like it dissolves right into the water, but it could take up, those particles are going to take up just a little bit of space in that solution. And so what you don't want to do is fill this up to 500 milliliters exactly with your water and then dump in your sodium chloride and mix it up, because then it will be not exactly 500 milliliters, okay? Or 500 cubic centimeters, I should say. So typically what they're saying here is you dissolve it in some amount of water that is less than the final amount you want, put it in your volumetric flask, and bring it up to 500. Okay, so that's what's happening here. So we're taking 50 grams of sodium chloride, we're dissolving it, and then making it up to 500 centimeters cubed, which is 500 milliliters. And we want to know the concentration of the solution, first of all, in moles per decimeter cubed, and then also in grams per decimeter cubed. Okay? So how would we get moles per decimeter cubed? What would be our first step? Amaya? I have 50.0 grams of sodium chloride. Yeah. Convert the grams to moles, exactly. So 50.0 grams. I don't want grams, because on the bottom, I want moles. Where am I going to get the numbers for this? Yeah, we need the molar mass. So sodium, what is it? 22 point, what is it on here? 99, thank you. And chlorine, 35.45. There's only one of each, so we can just go ahead and add them up. Oops. So that's going to be 58.44 grams per mole. Stupid thing is still not working. I've got to figure this out. Grams per mole. So where do we put the 58.44? On the bottom with the grams. And that is per how many moles? 1 mole. Okay. So we do that calculation. We end up with some number of moles of NaCl. Okay. And now, someone want to do that? Someone with calculation? Oh, Winnie, I see you're doing it. .856. Thank you for giving us the correct number of significant figures there. So that's how many moles we have, but we want moles per decimeter cubed. So how are we going to make this moles per decimeter cubed? Maya? Yeah, so this is what our final volume is. The 100 is just what you're mixing, what you're dissolving the salt in to start with. 500 is your final volume. It's being made up to 500 in that volumetric flask. So we've got to convert that to decimeters cubed. So we're going to divide by 1,000. We're going to end up with 0.5000 decimeters cubed. All right. Forgive my crappy board. All right. So then we just take this and divide it by that. 0.5000 decimeters. Someone want to? Oh, I see Lily's doing it. And if we're going to write it the way IB does, you would write that as mole dm to the negative 3. Draw a 3, that'd be great. There we go. Now we want grams also, grams per dm to the negative 3, grams per liter, which is a slightly different version than our moles per liter. So what am I going to do with that? How am I going to get grams per decimeter cubed? It's given to us in grams. So we're going to divide by our decimeters cubed, which we already know is 0.5. And that's going to give us what? Yeah, it's 100 because we only have 3 significant digits. How can I show that we actually have 100 with all 3 significant digits? You don't actually need to do this for a question like this, but, and this would be grams dm to negative 3. But, because if I just write 100, you don't know how many significant digits that is. You don't know that it's all 3. How could we write it to give all 3? Yeah? Yeah. So if we had to show sig figs here, we could make it 1.00 times 10 to the second grams. Oops. Again, if you write this as grams per liter or G/dm cubed, any of those things they will accept, but you have to understand what this means. Yes? 10 to the second? Oh, yeah, sorry, my 2 is a little bit cruddy here. Okay. All right, the worksheet that you picked up is for you to do on your own time. They are questions regarding molarity, and the answers are on the bottom of the back of the sheet. So you can check your answers, and if you have any questions about them, if you're not sure how to get those answers, you can feel free to ask. Yes? Sorry, hang on.